Let us talk about operations on matrices. So in the last section or in the last videos that we've had, matrices were used to solve systems of linear equations. Now, we are now going to look into matrix as an object in math which would have its own matrix theory and will have more applications of matrices. This would also mean that we are now going to look into matrix as an actual mathematical object which has its own language and properties. So, it is standard mathematical convention to represent matrices in any one of the following three ways. We can represent a matrix as an uppercase letter, a representative element enclosed in brackets, or a rectangular array of numbers like this. We are already used to this way of representing our matrix. But we can also represent a matrix such as this, especially in general definitions, or we can represent it like this. For example, if we're going to have matrix A with the elements 1, 2, 3, 4, 5, 6 here, so I can just simply write matrix A in my other notations or operations because this matrix A is the one that represents the actual matrix formed. So, let's take a look at some terminologies. We have what we call a column vector or a column matrix, and it's a matrix that only has one column. This one here. Those are examples of column matrices. If we have a column matrix, we also have a row vector or a row matrix. A row matrix is a matrix that only has one row. So for example, if I'm going to have this matrix 1, 0, this is a row matrix, a matrix that only has one row. Now, boldface lowercase letters often designate column vectors and row vectors. So for example, I would like to have my matrix A with the elements 1, 2, 3, 4 partitioned into two column matrices. I'm going to have my column matrix 1, 3 represented by A sub 1 and my column matrix A sub 2 represented by 2, 4. So we partitioned or divided our matrix A into two column matrices. Now, when we talk about any object in mathematics such as sets, variables, and now matrices, we would usually start with their equality. So we say that two matrices, A and B, are equal when they have the same size and the same elements for any row and column out there. So that is what this definition would mean. They have to have the same size and same elements in their exact positions. For example, let us consider the four matrices. A with elements 1, 2, 3, 4. B with elements 1, 3 for columns. C with elements 1, 3 in the rows. And D with the elements 1, 2, X, and 4. Now, immediately, we can say that matrix A is not equal to B, A is not equal to C, because they are of different sizes. Remember, matrices should be equal if they would have the same sizes. That's the first condition. Now, matrix A and matrix D can be equal. However, we have to be sure that their entries are exactly the same, apart from their sizes. We know that A and D have a similar 2 by 2 size, and the elements of A will be 1, 2, 3, 4. The elements of D, 1, 2, X, 4. 1, 2, and 4 are already secure. If we can say that this is equal to 3, then we can say that A is equal to D. So in this, we're just going to state that matrix A is equal to D if and only if X is equal to 3. There will be cases wherein you'll be asked something like this, but remember, for matrices to be equal, they should have same size and exactly the same entries.